Hey guys, my name is Tensor. Welcome back to the Golang blockchain tutorial video series. This will be part 4 in the series. Today we'll be implementing a very basic version of transactions into our blockchain. Because transactions are a fairly difficult topic, I will be splitting up this topic into multiple different videos. Also, I just wanted to let you guys know that I'm using a new font. If you guys find that this font isn't very readable, please feel free to let me know in the comment section below. Let's start out here by defining a new file called transaction.go inside of our blockchain module. And then inside of this file, we'll define our basic transaction structure. Inside of a blockchain, transactions are made up of inputs and outputs. And as you can see here, our structure has an ID, which will be a hash, and then it has an array of inputs and an array of outputs. Now, because a blockchain is an open and public database, we don't want to store any kind of sensitive information inside of the blockchain. There are no accounts inside of our transaction, no balances, no addresses, no coins, and no senders and receivers. Instead, everything is done through these inputs and outputs, and then we can derive all these other things from the inputs and the outputs. Now, our output struct is fairly simple. Each output has a value assigned to it, and this is the value in tokens, which is assigned and locked inside of this output. And then we have what's called the pub key. Now, the pub key is a value that is needed to unlock the tokens which are inside of the value field. On the Bitcoin platform, this pub key is derived through a fairly complicated scripting language called script. But for our first implementation of these transactions, we will not have anything like that. So we'll just use an arbitrary key to represent the user's address. So if the user's address is, for instance, Jack, then the pub key will be Jack. And that will allow the user to unlock the tokens which are inside of this output. Another important part about these outputs is that they're indivisible. This means that you can't reference a part of an output. A good metaphor for this is if you walk into a store and you buy $5 worth of goods and you give the cashier a $10 bill, the cashier can't just rip the $10 bill in half and hand you the other half back. Instead, they have to give you back a $5 bill. So if there are 10 tokens inside of our output, we need to create new outputs, one with 5 tokens inside of it and another one with 5 tokens inside of it. Inputs, on the other hand, are just references to previous outputs. We have 3 fields inside of our input. We have an ID field, which references the transaction that the output is inside of. And then we also need to know the index where this output appears, which is this out field. So if a transaction has 3 outputs, and we only want to reference one of them inside of that transaction, then we say, okay, transaction X at index 2, and that will be the output that we're referencing with this input. The last field inside of the input is similar to the pub key in our output. The sig is a script which provides the data which is used in the output's pub key. Now, of course, because we do not have the script logic in place, the sig is just going to be the user's account. So like we said before, if we have an account named Jack, then we're going to push it into the sig as well as the pub key, so that Jack can then unlock the output which is being referenced by the input. In our blockchain, we have our Genesis block. In that block, we also have our first transaction. This is what's called a Coinbase transaction. Now, interestingly enough, in this transaction, we have only one input and only one output. And the input inside of it, rather than referencing an older output, because there are no older outputs, just references an empty output. It also doesn't store a signature. Instead, it stores a bunch of arbitrary data. The Coinbase also has what's called a subsidy or a reward attached to it. This reward is released to a single account when that individual mines the Coinbase. In our implementation, we're just going to add a constant for our Coinbases, and we're mainly just doing this to make things simpler for now. Let's build a Coinbase function. So we need to pass in the to account address and then the data which we want to put into the Coinbase. And both of these are strings. And this outputs a pointer to a transaction. If the data variable is empty, then we'll create a new data variable using fmt fsprintf, which will just say coins to, and then we'll put in the account name. We then need to define the transaction input for this Coinbase and the transaction output for this Coinbase. The transaction input is referencing no output, so it has an empty slice of bytes for its ID. Then the out index is -1 because again it's referencing no output, and then the signature is just the data string. The output, on the other hand, has the reward, which is 100 tokens, and then the pub key string for this output is a reference to the to address which we're passing in here. So when we create our blockchain, if an account named Jack mines this block, then Jack will get 100 tokens. Now we can instantiate our transaction struct. We can put in nil for the ID and then put in the input and the output. And then we'll call a method called setID, which will create the hash ID for this transaction. And then we'll return the reference for this transaction. The setID method is fairly basic. We just want to create a hash based on the bytes that represent our transaction. So we create a bytes buffer, and then we want to use the gob new encoder, and we use the encoder to encode our transaction. Then we handle any error that we get back from that action, and then we hash the bytes portion of our encoded bytes, and then we set that hash into the transaction ID. Before we leave this file, we need to create a few more utility functions which will allow us to determine what type of transaction we have and whether or not we can unlock an output or an input that's referencing an output. So first let's create a function which will allow us to determine whether or not a transaction is a Coinbase transaction. This will be a method on the transaction struct, and it will output a boolean. First, we'll check to see that the length of the inputs is equal to 1 because the Coinbase only has one input. Then we'll check to see that the first input in the transaction's ID is equal to 0. So the length of this input's ID will be equal to 0. And then we want to check that the input's out index is equal to -1, which we set up in here. If all of these come back as true, then we have a Coinbase transaction. Now let's create the two methods which we need to unlock the data inside of our outputs and our inputs. So for the input, we just take the string of data that's being passed in here, and we check to see that it's equal to the signature that's attached to the input struct. And then for the output, we do the same thing except with the pub key. If these come back as true, then that means that the account, which is the data, owns the information inside of the output, or it owns the information inside of the output which is referenced by the input. Now that we have our transaction struct set up and we have the ability to create a Coinbase transaction, we need to add transactions to our blocks. So whereas before we just had a nondescript data field inside of our block struct, we can now replace it with an array of transactions. Now it's important to note that each block needs to have at least one transaction inside of it. And each block can have many different transactions inside of it as well. Now as soon as we change this field, you'll notice that we get a bunch of errors. Particularly, we get errors with our create block function and with our genesis block function. We can go ahead and fix these errors. With the create block function, we can just pass in an array of transactions and then put that array of transactions directly into the block declaration. And then with the genesis function, we can pass in a transaction, which we'll call Coinbase, and then we can call create block, pass in an array of transactions with only the Coinbase inside of it, and then pass in an empty slice of byte. Before we move out of this block.go file, we need to consider that our proof of work algorithm must consider the transactions that are stored in a block. So we'll create a new function called hash transactions, which allows us to use a hashing mechanism to provide a unique representation of all of our transactions combined. So here we'll create a variable called txHashes, which will be a two-dimensional slice of byte, and then we'll create a slice of byte with a length of 32. We'll then iterate through each of the transactions inside of a block and append each one to the two-dimensional slice of byte that we created up here. And then we'll use the bytes join function to concatenate all of these bytes together, and then we'll hash them with our SHA-256 sum256 function to create the hash. Now if we go inside of our proof.go file and go into the initData function, we can call to the hash transactions method that we just created to hash the transactions in a block and concatenate them with the rest of the block's data. Let's now go inside of our blockchain.go file, and we want to add two new constants to this file. We want to add a db file constant, which points to temp blocks manifest, and this is a constant that we can use to verify whether or not our blockchain database exists. When Badger creates a database inside of a folder, it creates this manifest file. The next constant is called Genesis data, and as I mentioned before, because the Genesis block needs to have a set of arbitrary data in the input signature, this will be that arbitrary data for our implementation. Now down here we have our init blockchain function, and I want to split this function into two separate functions, and we can split it by the if statement. So currently we have this if statement which is checking to see if the blockchain exists. First, let's create a little helper function which will allow us to determine whether or not the Badger database exists. We can do this by calling osstat on our db file, which is our manifest file, and if we get back an error that is not exist, then we can return false, otherwise we can return true. Now with this helper function, we can split up our init blockchain function into two separate functions. Notice that the init blockchain function now takes in an argument. In this case, it's an address, which is just a string. And then we run an if check to see if the database exists. If it does exist, then we print out that the blockchain already exists, and then we exit the program with a runtime go exit. If the database doesn't exist, then we want to run through this as normal. So we set up the Badger default options, the database path, and then we open up Badger. Then we run our update transaction, and inside of this update transaction we now want to create our Coinbase transaction with the address that we're passing through and then the constant Genesis data value. Now the address that we're passing through is the address that will automatically mine this Genesis block. So that address will be rewarded the 100 tokens. We can now take the Coinbase transaction and pass it into our Genesis function to create the Genesis block, and then we'll continue as we did before, where we put the Genesis block into our database and serialize it, and then we also get the Genesis block's hash and put it into the last hash key. Here's the second function that we created out of our original init blockchain function. This one's called continue blockchain, and again it takes in an address, which is a string. We check to see if the database exists equals false, meaning the database does not exist, and if it doesn't exist, we print out that it doesn't exist, and then we exit the program. Otherwise, we run through everything as we did before, where we're creating the default options, the DB path, and then opening up Badger. And then we run our DB update. We get the last hash from our database, and then we put it into a new blockchain instance with our last hash and database and return it from the function. By splitting this function into two, we can now easily create the functionality that we need for our command line interface to be able to check the amount of tokens that are assigned to an account, as well as be able to send tokens from one account to the next. Now the first step in adding these pieces of functionality is creating a way of finding all of the unspent transactions which are assigned to an address. Unspent transactions are transactions that have outputs which are not referenced by other inputs. Now these are important because if an output hasn't been spent, then that means that those tokens still exist for a certain user. So by counting all of the unspent outputs that are assigned to a certain user, we can find out how many tokens are assigned to that user. So let's create this method, which will be called findUnspentTransactions. It'll take in the address, and it'll be a method on our blockchain struct. It'll output an array of transactions as well. We'll come in here and we'll create our array of transactions, and then we'll make a map where the keys are strings and the values are slice of integers. And then we'll use our blockchain iterator to be able to iterate through our blockchain, which is in the database. So as we did with our other iteration function, we create a for loop, we get the first block out of the database, and then we break out of the for loop if the length of the block's previous hash is equal to 0, meaning the block is our genesis block. Inside of this for loop, the first thing we want to do is iterate through each of the transactions inside of a block. And we'll take the transaction IDs from each of the transactions and encode it into a hexadecimal string from the byte representation that already exists. Now for each of the transactions, we want to create another for loop which iterates through all of the outputs inside of the transaction. Also notice that I'm adding a label to this for loop, and that's so that we can break from the inside to this portion of the for loop and not break out of these other two for loops. As we're iterating through each of the outputs, we want to see if the output is inside of our map. So we check to see if the map with the transaction ID as a string is not equal to nil. And if it's not, then we want to iterate through the map, and we want to see if the spent out, which is the index, is equal to the output index that we're iterating through here. And if it is, then we just continue with our outputs for loop. We then need a way of determining whether or not this output can be unlocked by the address that we're searching for. So we use our outCanBeUnlocked method, and we call it on our address, and then we take each of the transactions that can be unlocked by this address and put them into our unspent transactions variable. Now finally, outside of this for loop that's iterating through the outputs, we need to check to see if the transaction is a Coinbase transaction or not. And if the transaction is not a Coinbase, then we want to iterate through the transaction's inputs. So this is a way for us to find other outputs that are referenced by inputs. And if we can find the other outputs, then we can check to see if we can unlock those outputs with our address. And if we can, then we want to put them inside of our map as well. So we take the input's ID and we encode it to a string, and then we append that out index to our map. Now finally, at the end of our function, we just pass back the unspent transactions array, which will have all of the unspent transactions which are assigned to the user account which we pushed through this function. Let's now use this method to be able to find all of the unspent transaction outputs which correspond to an address. So again, this is a method on the blockchain. We pass in the address, which is a string, and then we output an array of transaction outputs. We call our findUnspentTransactions with the address inside of it, and we pass this into a variable called UnspentTransactions. And then we want to iterate through these unspent transactions. And then inside of each of the unspent transactions, we want to iterate through all of the outputs in the transactions. And we want to check to see if the outputs can be unlocked by our address. And if they can, we'll add them to our unspent transaction output variable, and then we'll return that variable. There's one final method that we need to create to make all of this work properly, and this method will enable us to create normal transactions which are not Coinbase transactions. Because up until now, all we can do is create Coinbase transactions. The other functions that we've defined will allow us to find the balance of a user's account, but we have no ability to send coins from one account to another. For this to work, we need to find all of the unspent outputs and then ensure they have enough tokens inside of them. And that's what this method does for us. So this method is on the blockchain. We pass in the address that we want to check and then the amount that we want to send. And then this method passes back a tuple of an integer and then a map with a string as the key and then an array of integer as the values. We then need to define 3 different variables. First one being the unspent outputs, which is just the map. Then we'll have the unspent transactions, which we can get by calling find unspent transactions on our address. And then we'll have a variable called accumulated, which we'll set to be 0 by default. Now the first thing we want to do is iterate through the unspent transactions, take the transaction ID, encode it into a string, and then we need to go ahead and iterate through all of the outputs inside of these unspent transactions. As we're iterating through each of these outputs, we need to check if the output can be unlocked by the address and if the accumulated is less than the amount that we want to send. Now the reason we need to check this is so that we can't make a transaction where the user doesn't have enough tokens in their account. If these two come back as true, then we want to increment our accumulated value by the output value, and we want to add our output index to our output map, and then we'll break when the accumulated is greater than or equal to the amount that we want to send. And notice that I've also marked this for loop with a label as well so that we can break out of both of the for loops. Now finally, at the end of the function, we just want to return our accumulated and then our unspent outputs. And we'll use these two values to generate the general transaction. Before we leave the blockchain.go file, we do want to fix the add block function. Now notice this is still taking in a string when it should be taking in an array of transactions. We can correct this, of course, by just passing in our array of transactions and then taking those transactions and passing them into the call to create block. And that will, of course, get rid of any of the errors inside of this function. Now let's go back into our transaction.go file and create a function called new transaction. For this function, we pass in 2 strings. We want to pass in the from account string and the to account string. Then we want to pass in the value that we want to send. And then we need to pass in a pointer to our blockchain. And then the function will pass back a pointer to a transaction. We'll create 2 variables, one for the inputs and one for the outputs. And then we'll call our find spendable outputs function on from and on amount. And then we'll get the accumulator and then the valid outputs. We can do a quick check to see if the amount is greater than our accumulator, and if it is, then we can just panic and say that the account doesn't have enough funds, and this will just shut down the entire application. If we do have enough funds, however, we want to iterate through our valid outputs. We'll take each of our valid outputs and we'll decode the string ID into bytes, and then of course handle the error. We then want to go through each of the outs, which is the range of outputs that we were iterating through, and create a new input for each of the unspent outputs. And the input that we're going to create will have the transaction ID inside of it, the out value, and then the from address. Then we'll take each of these inputs and append it into our inputs variable, which contains all the inputs for this transaction. So essentially we're creating an input for each of the unspent outputs in this transaction. Now we need to create the outputs for this transaction. So we've got a bunch of inputs, and first we'll create the first output. So outside of our for loop, we'll create our outputs by creating an output with the amount that we are going to send, and then the to address, which is the person that we're sending to. And then if the amount is less than the accumulate, which means that the amount that the from user has is greater than the amount that he's trying to send, then we want to create a second output. So the first output is the transaction where the user is sending, say, 50 tokens to a new address. And then the second output is created if there are any leftover tokens in the original sender's account. Finally, for this function, we can just instantiate a transaction and pass in our inputs and outputs, and then we can call transaction setID to get the hashed ID, and then pass back the reference to this transaction. Now that we have this fairly basic transaction system inside of our blockchain, we want to create some commands inside of our command line interface so that we can create new transactions with our blockchain. The first thing that I want to do is simplify the command line by removing the blockchain from the structure. And then we want to add to our print usage function. So before we just had the add block command and then the print chain command. Now we're just going to get rid of the add block command and then add 3 new commands. First we have the get balance command where we pass in an address, which is just a string, and then we get the balance for that address. Then we have the create blockchain command where we also pass in an address. We create a blockchain and then that address mines the genesis block of that blockchain. Then of course we have our print chain command, which just prints the blockchain. And then finally we have a send command, which allows us to send from an account to another account, and then we can specify the amount that we want to send as an integer. We can leave our valid arguments function alone, and we can remove this add block function because we don't have this functionality anymore. For the print chain method, we're just adding a few little things just to make this work. We need to instantiate a blockchain by calling our continue blockchain function, and we'll pass in an empty string. Then we'll defer the closing of this blockchain and then create our chain iterator. Then for the for loop, where before we were printing out the data inside of the blockchain, we just removed that line and we kept everything else. Now let's add a method which will allow us to create a blockchain. This method will just call the init blockchain function with the address inside of it. And of course, as I said before, that address will be the person who mines the genesis block. And then we'll immediately call chain database close to close the database. And then we'll print out that we've finished this operation. The get balance function will be fairly simple as well. We'll open our blockchain by calling continue blockchain on the address that's being passed into here. Then we'll defer closing the database again. We'll create a variable called balance and set it equal to 0. And then we'll get all of the unspent transaction outputs for the address and assign them to this variable. And then we want to iterate through that address and get all of the values out of our outputs and increment our balance by those values. After we finish going through all the outputs, we can then print out the balance with the address inside of this string. So it'll say balance of such and such account is such and such amount. Finally, we need a method to allow us to send tokens from one account to another. This method takes in the from and to string, and then it takes in the amount that we want to send. We call the continue blockchain function with from inside of it, and then we defer the database closing function. We want to create a new transaction with from to the amount and then the chain reference. And then we'll call chain.addBlock with this transaction inside of it. And then finally we'll print out success when this finishes. Now we can add to our run method, and we're just going to add the different commands that we now have. So we have our get balance command, our create blockchain command, our send command, and our print chain command. And then we'll add the substrings and subintegers. Then we'll run through our switch statement again, and then we'll just check to see which command has been parsed. Now finally, to finish things off, we just want to simplify our main function. And we can do all of this because our command line does not connect to our blockchain anymore. So instead of instantiating a blockchain, we can now instantiate just the command line and then call command line.run. So now let's go ahead and run our create blockchain command with the address of John inside of it. As you can see, this will generate the genesis block, then come back and say genesis was created, and then come back and say finished. We can go ahead and print the chain, and you can see here it's got the one block, which is just the genesis block. And now we can go ahead and check the balance of our John account. And you can see balance of John is 100 tokens. Now let's send 50 tokens from the John account to an account called Fred. You can see here it creates a new block and then it proves it. And to show this, we can print out the actual blockchain. You can see we have the 2 blocks here. And then we can check the balance of Fred, which will come back with 50 tokens. And we can also check the balance of John, which will also come back with 50 tokens. Alright guys, well that's it for our tutorial today. I know I kind of rushed through the whole command line part of the tutorial, but that was because we sort of covered everything about the command line interface in the last tutorial. If you enjoyed this video, feel free to subscribe and like. If you have any questions or comments, feel free to leave them in the box below. And if you dislike this video, then by all means downvote it as much as you like. Have a good night.